Hi, we've had a question come in from Jed from Houston in Texas. What north references can be used for a wellbore survey, and what do we use to convert between the different north references we have? So let me just firstly start by drawing three lines. So I'm going to have a grid north, I'm going to have a true north direction, and I'm going to have a magnetic north direction, and here we're going to have our wellbore direction. So how we can describe the azimuth of the wellbore can be with respect to true north, it can be with respect to magnetic north, or it can be with respect to the grid north. So I'm going to have three different potential angles describing the azimuth of the wellbore from each of the three north references that we have. And the way that we can convert between the different types of north references is, for example, between the grid north and true north, I have an angular relationship which is going to be known as grid convergence, and between true north and magnetic north, I have another angular relationship that will be known as magnetic declination. So the way that I would convert between grid north and true north is by application of the grid convergence angle, and to convert between true north and magnetic north, describing the wellbore azimuth, I would apply the magnetic declination. What we'll run through now is a little bit more in-depth description of both the grid convergence and the magnetic declination, and then we'll run through one worked example to show how these angles actually relate to one another. So let's start by looking a little bit more in depth at the grid convergence. Now, grid convergence applies to the type of map projection that we're going to be using to describe the easting and northing and the latitude and longitude of the surface position of the well header. So in this case, I will have a map projection which will be orientated towards grid north. And on here, I will have my grid itself, which we can draw thus. I then, on top of that, can superimpose some other lines, which will be my graticules, which will show then the relationship between grid north and my true north direction. So I'm going to get a diagram that's going to look something like this. My centre line here will be known as my central meridian. The blue lines here are going to show how true north will converge towards the North Pole for both being west of the central meridian and east of the central meridian. And therefore the angular relationship I can see between my grid north direction and my true north direction at any point within the diagram that I've drawn here, these will be my convergence values that we can compute. Now, what we want to quickly look at then is firstly how we compute the grid convergence, and also then just to draw to your attention that the way that we can calculate grid convergence is going to be based upon the type of map projection that we're using. So it's going to be different for a transverse Mercator, which will be the example we'll go through, versus how we would compute it for a Lambert conic conformal. So let's just take that, and now I'm going to introduce you to a simple equation, which is going to be that the grid convergence is going to be computed from the following expression, where my delta lambda will equal my central meridian minus my longitude. So there are two important things that I can circle here. First is going to be the latitude, and second will be the longitude. So if I take the position of a wellbore, let's just say I'm going to take a wellbore that's going to be right at the very edge of my transverse Mercator mapping zone, and I'm going to assign coordinates to that wellbore, which are going to be 30 degrees north and 102 degrees to the west. So that's going to be my physical position of my point. Now, in order to go through this computation, I need to know what type of map projection I'm going to be using. So in this case, we'll be using the transverse Mercator. And I'm going to be applying this conversion of UTM 14 degrees north. And secondly, there are two different conventions for convergence. Both give the same answer, but a different sign convention. And the convention that we're going to be applying during these computations is going to be known as the Gauss-Bomford convention. And I'll show you a little bit more about this in 1 second with respect to the sign. So let me first and foremost then calculate a value for grid convergence using the expression that we've got. Now the reason I had to specify that we're in UTM zone 14 north is because the central meridian, which is given by this part of the expression here, needs to be known. So for UTM zone 14 north, we have a central meridian that is going to be 99 degrees to the west. I have got a point that I also know here in terms of longitude of my wellheader, which is 102 degrees west. So the first thing that I can compute is my delta lambda, which is going to equal my central meridian, which is going to be minus 99, because I'm in the Western Hemisphere, minus a minus 102. So my delta lambda then will give me a value of 3 degrees. That being because that will, two negatives cancel out to be a positive. Now, the second thing that I know in terms of my position is that my latitude is given as 30 degrees north. So I can now input delta lambda and also my longitude into the top expression here to calculate a number for the grid convergence. So in this particular case then, my grid convergence is going to equal minus the sine of 30 degrees multiplied by my delta lambda, which is going to be 3 degrees. So, just from some simple basic trig, I know that the sine of 30 degrees is going to be 0.5 with a negative number there. So my convergence will be minus 0.5 times 3, which is going to give me a grid convergence of 1 degree and 30 minutes. So that basically means that this angle here between true north and grid north will be 1 degree and 30 minutes. Whoops, and we need to put the negative sign in front of there, which we'll then come on to. Let's just keep that number then in our heads for now, and we'll see how that then is used within the worked example we will give in a few minutes. Now, one other thing we mentioned there is that we need to be cognizant of the sign convention and also the sign that we apply to the grid convergence. Now, I just want to quickly draw a simple diagram for you, which will show how the sign of convergence will vary between the different quadrants we can find ourselves within when we're on the Earth and we're mapping parts of the Earth. So let me start by describing that horizontal line there as my equator. I'm going to describe this first vertical line here as my longitude of Greenwich, and then the two other vertical lines will be the value of the central meridian, which is going to be in the eastern hemisphere north of the equator and in the western hemisphere north of the equator. So I am going to write on here now negative, positive, positive, negative, positive, negative, positive, negative. So you can see within each of the quadrants that I've got within the screen there, what sign convergence value should take depending on where my wellhead is in respect to the quadrants that we've got here. So for example, in the case that we're going to follow, my wellheader is going to be 102 degrees longitude in the western hemisphere. My central meridian was 99 degrees for UTM zone 14. So therefore, I am going to be west of the central meridian in the Western Hemisphere. Therefore, I should end up with a grid convergence with a negative sign, which is exactly what we're showing within this expression that we've got here. Okay, so that is enough just for now about grid convergence, or the angular relationship between my mapping surface north and the true north of the Earth. The second correction factor that we've got when we can convert azimuth between to describe the different azimuths of a wellbore is going to be a figure known as magnetic declination, which is typically given the sign Greek delta. Now, magnetic declination is a wee bit more complicated than grid convergence for a number of factors. So let me first start by drawing my wellheader position, which I know is going to be 30 degrees to the northern hemisphere and to 102 degrees in the western hemisphere. Now, when I calculate magnetic declination, which is going to be my relationship between true north and magnetic north, I also need to introduce, in order to derive the value of declination, not only the geospatial position of where my wellhead is, but I also need to bring into account a third piece of information, which is going to be an epoch date. And the reason we need an epoch date is because the magnetic north, or the magnetic north pole, wanders. It is not in a static position. So the very fact that it wanders means that declination is going to vary year by year, and therefore by taking into account and specifying declination correctly, I need to give the date of the year and the month in which we are going to calculate magnetic dec for the geospatial position that we provide. So in this case, I'm going to have a well that is going to be from May 2019. Now, what we will do is we will place the position and the date into a magdec calculator, a magnetic declination calculator, and out of the calculator will come two pieces of information. The first piece of information to be returned will be the actual value of the magnetic declination for the position we provided and the year in which we are specifying for the epoch. And the second piece of information that we're going to get is going to be a rate of change. And the rate of change is going to tell me by how much this value of declination is going to be changing on a year-by-year basis. And again, that rate of change will apply specifically to the geospatial position I provided for the wellbore header, and again, the date which I am providing. So if I put in 30 degrees north, 102 degrees west for a epoch date of May 2019, I am going to get a magnetic declination, which is going to be given as 5 degrees and 52 minutes. This is approximate 5 degrees, 52 minutes east, with a rate of change of 6.7 minutes per year in a direction to the west. Now, just keep that information again in your minds there, because we're going to apply this within the calculation that we're going to be performing in a short while. I just want to just draw one other diagram for you, just to hopefully clarify a couple of things. The first line I am going to draw is going to be known as the agonic line. And the agonic line is a theoretical line that's going to have a value of 0 degrees, which is effectively going to be where magnetic north and true north are the same along this line here. To the east of the agonic line, I am going to have a series of contours, and these contours will then show me what the value of magnetic declination will be along those lines that I've drawn. To the west of the agonic line, I can have another series of contours that will show me the value of magnetic declination to the west of the agonic line, as we have shown. So that is going to be the picture that we're going to see of how magnetic declination is going to be changing. And I've drawn this to try and emulate as closely as I can from my memory what the magnetic declination will be like over the area of Texas. So I have got a well that's going to be with a well header over here of 30 degrees to the north and 102 degrees to the west. And we were given a value of declination that was approximately 5 degrees and 52 minutes to the east. So that's going to be a positive value to the west of the agonic line that we've shown. Now I can quickly draw two diagrams here. I've got a line there which is true north, magnetic north, and then the direction of my well bore. So I'm going to get this relationship shown to the west of the agonic line, and I can draw a very similar diagram that will give me magnetic north, true north, and well bore azimuth to the east of the agonic line. Okay, so just take into consideration this diagram as well before we now head into a simple worked example to show the relationships between grid north, magnetic north, and true north, and how we can describe the azimuth of a well bore using any of the three north references that we've described here. Now, before we just quickly dive into the worked example, I need just to provide a couple of other very simple expressions or equations to you. And these are going to be as follows. So, the first expression we need to describe is going to be how we will relate grid north, true north, and grid convergence. So we're going to say that grid north will equal true north minus grid convergence. And therefore, true north will equal grid north plus convergence. Secondly, I can write down that magnetic north is going to equal true north minus magnetic declination, and thus true north will equal magnetic north plus magnetic declination. Let me take those two expressions there, and further I could write grid north plus my grid convergence will therefore equal my magnetic north plus my magnetic declination, and by simply rearranging this expression here, I can say that the grid north is going to equal magnetic north plus declination minus my grid convergence. So just keep a note of these expressions here, and we'll come back to these now within the worked example to basically show how these correction factors can be applied between the three north directions that we've described. Let me go back to a diagram that I started with at the beginning, and I'm going to just leave this over here. So it's going to show that my grid north, my true north, and my magnetic north directions in relation to a well bore path. So that's going to be the azimuth, the physical azimuth of the well bore itself. What we need to have now is the azimuth of this well bore given in respect to each of these three north directions that we've got. Now, for simplicity of the calculation, I am going to assume that we know the azimuth of the well bore with respect to true north, and that angle is going to be given as 90 degrees. So that's the first piece of information that I know. I now want to know what the azimuth of the well bore is going to be with respect to magnetic north, and also then with respect to grid north. So let us go over here, and we can write down the expression that grid north equals true north minus my grid convergence. And if we cast our mind back earlier, we were told that the convergence value is equal to -1 degree and 30 minutes. That was what we calculated earlier in the answer. Therefore, grid north is going to equal 90 degrees minus -1 degree 30 minutes. So therefore my grid north is going to equal 91 degrees and 30 minutes. Let me just go back to my diagram and we can see that that is going to be the angle of grid convergence, and therefore for the arrangement that we've got here, grid north should have a larger value than true north when we're describing the azimuth of the wellbore. So that kind of pans out as being correct against our diagram. Secondly, we know that magnetic north is going to equal true north minus magnetic declination, and we were told that the value of magnetic declination was approximately equal to 5 degrees and 52 minutes to the east, so positive. And again, substituting the numbers into this expression here, we're going to find out that magnetic north will equal 90 degrees minus a positive figure of 5 degrees and 52 minutes, which means that my wellbore is going to have an azimuth with respect to magnetic north of 84 degrees and 8 minutes, just by subtracting those two figures there. Okay, and that bears out again with the diagram here that magnetic north is going to lie to the east of true north for the area that I'm describing. So remember that point there is going to be my wellheader location, or 30 degrees to the north and 102 degrees to the west. And we can now see that I've got the relationship shown for the three north directions and values now for true north, which we said was 90 degrees. We've now calculated what the well azimuth would be with respect to grid north, and the well azimuth would be respect to magnetic north. And if we apply that last expression that we got to, which was grid north equals magnetic north plus declination minus convergence, let us now just plug these numbers into this expression here, and we can then get back to grid north using the three variables that we've got on the right hand side there. So in that case then, grid north will equal magnetic north, which is 84 degrees and 8 minutes, plus my magnetic declination, which is 5 degrees and 52 minutes, minus 1 degree and 30 minutes. So that is all going to cancel out there and is going to give me a value of 7 degrees and 22 minutes. And if I add that now to my magnetic north azimuth there, I will end up with a figure that grid north will equal 91 degrees and 30 minutes, which returns me back to the figure we calculated there. So to recap, the wellbore azimuth can be described with relation to true north, grid north, or magnetic north, depending on what type of survey tool we're going to be using during the wellbore survey. And we have two correction factors, which are going to be known as the grid convergence and the magnetic declination, which will allow me then to re-describe the azimuth of the wellbore in relation to a north of my choice. Hopefully, Jed, that answers your question. Thank you.